Thank you, Bill. That was extraordinarily nice, and I appreciate it. And let me return the favor by giving my deep appreciation to both Bill and John for what they've done for me personally and for Software. I've gotten wonderful support from WTBC, from John Benson, and also from Christine Langley and Jeff Lowe in nurturing my company, and then today from Fred Schmeckel and John Dick in giving a decent PowerPoint presentation. And I promised I wouldn't talk about food poisoning because of the hour, and so I'll talk about other parts of my company. So let's suppose you have a loved one, say your mother, in the hospital who's had surgery. And due to complications, possibly the hospital wasn't using the most stringent aseptic technique, which happens more often than we'd like to admit. She has acquired a blood-borne infection. And so after a period of time, possibly because your mother is suffering from some immunocompromised state, she starts to go into septicemia and then septic shock. And so when that starts to happen, the physicians will take the blood and put it into some sort of diagnostic machine or protocol for analyzing the blood. And if it's bacteria, they will at the same time give a broad spectrum antibiotic with the assumption that that is going to kill the disease. And most of the time that works, 90% of the time. 10% of the time it doesn't because it's a fungal infection. And if the antibiotic doesn't work, the next step is to then culture the blood sample in a medium that is sensitive for the growth of fungus. And 3 days later, after starting that, if it seems that fungus is growing, they can then try to analyze it for the species of fungus and determine the best drug therapy. Unfortunately, 40% of the patients who die from blood-borne infection die from fungal infection because that takes far too long. So the problem is fungal detection in blood. How can we do that more rapidly? Septicemia, or blood infection in general, is the 10th leading cause of death in the U.S., and that is all sources of death. And has the third highest mortality rate among infectious diseases, with the first two being pneumonia and tuberculosis. 40% of the deaths due to blood-borne infection are due to fungal infection. And the annual hospital costs to deal with this are about 16.5 or 16.7 billion a year. I know that doesn't seem like much compared to the federal budget. Anyway, the current time to detect fungal infection is 3 to 6 days. It's much faster for bacterial infection. So the real, I hate to use the term killer application for us, is fungal infection, and I mean that literally. So what my company has attempted to do is to provide a high-speed system for doing fungal detection that's sensitive to individual fungal cells, that can do the detection in 1 to 2 hours and not 3 to 6 days, that can detect not only the fungus, a fungus being present, but also to detect the species. And in the course of doing so, we'd like to do something that's economical and robust and easy to use. So we developed a device which I have patented through the university and licensed back to my company, Software, a prototype which we've used for doing we've used for doing testing in the laboratory, and basically have determined that the system works and the concept is valid and it needs to be followed up with additional FDA-approved tests. So the way it works is the following. You follow the cartoon, the cells are pumped into the system. So you start with a 5 or 10 milliliter blood sample from the patient that's extracted bedside, put it into a little container, add a dye that's fungal specific, let that incubate for a few minutes, then you pump it into my system, and it takes a few minutes to pump through the system and for the detections to be made. And so it goes into this cell, and the little green dots are supposed to represent fluorescing cells. And those are lit up with an LED, that incredibly bright LED, which are now on the market, which light up the cells through a window, and then a digital camera, the kind that I used to use for astronomical observations, and a 35mm lens, not a telescope, are used to image the cells in real time as they flow through the system. And you can see the same thing on the left. The sample would be over here. It's pumped into the system through this white hose, goes through the optics. Here's the pump, and then goes out of the system into a waste container. It's fairly simple and straightforward, except for the software. The secret sauce is all of the software, of course. Here are the guts. Right here, in panel B, you see the guts. Here's a flow cell, a mirror, an LED that's air-cooled, and a little lens that focuses the LED onto the detector. Very simple to make, and we have a patent on that. This shows what the camera would see. So the test is being done, the blood is being pumped through the system, the LED is doing its work, lighting up the fluorescent bugs, microorganisms in the blood, and the fungus would appear to be these bright dots. And so this is a digital image. This ring is the orifice or the hole through which the sample is being pumped. And here you see the cartoon of the sample flow. This is where the camera focuses, this bright bar, and then it goes out into the waste container. And so this is what you see, and we have software, not a human being, but software that automatically does all the counting of the bright particles as the material is flowed through the system, and it works. Here are a couple of images of the same thing. Again, on the left is another view. You get a sense of the scale of the size. This is a 6-inch ruler, so it's not that big. And then on the right, you can get some idea of how bright the LED is. And we don't even have, that's turned on at about 10% of the power. It's blindingly bright. It costs about $40. So the technology has gone through leaps and bounds since we first started our experiments. So we run the system through first with a fungal dye, which lights up in the presence of the cellulose or chitin in the cell wall of the fungus. And then if we've identified a fungus in the blood, we then take a dye from a company in Massachusetts that produces a specific RNA dye that's species specific and will light up different colors depending on the species of the fungus going through the system. So the second trip through, we can do species identification. You see an example of that in this slide. There's a company in Norwood, Massachusetts called AdvanDX that we collaborate with. And they produce, for example, a set of stains that will dye one species of Candida, Candida being the fungus that most all of us have on our arms and legs, inside of our mouth. We just don't know it, and it really doesn't hurt us unless it gets penetrated through our skin into our bloodstream. But here are two pathogenic forms of Candida, and one of their dyes turns it red, another one turns it green, and you can have a cocktail of a number of different dyes that will turn different species, different colors. And so they have what they call a stoplight cocktail that turns red, green, or yellow, depending on the pathogenicity of the species. Red is bad, green is good, yellow as well, we don't know. So why is this important? Well, this graph shows a survival rate after a patient has severe enough septicemia that it starts to become really obvious, like they're going into septic shock. And this shows a survival rate versus time, the amount of time when drug therapy, appropriate drug therapy, is initiated. So in other words, if the person has fungal septicemia and you give them an antibiotic, that's not appropriate, and they would still continue to fall along the graph until at 36 hours the survival rate becomes minimal. So this first hour after the onset of septic shock has been termed by physicians as hour, because it's the one golden opportunity you have to help your patient survive. And so time to diagnosis is critically important, and this is one difficult problem that still exists in medical treatment of septic patients. So in summary, this particular product that we're developing, the benefits to the patient are obvious. It would be a life-giving solution to the fix that they're in. The benefits to the hospital, under current Medicare regulations, hospital-acquired infections, the cost cannot be passed on to the insurance company, to Medicare, or the consumer, so the hospital has to eat it. And so they have two solutions. One is to use better septic technique, and two is to use better diagnostic techniques so that the patients can be treated more efficaciously. So the patent that we have on this device, it's what I call a platform device. It can be used to solve a number of different problems. I've given you one application for which we've received NIH funding. We have 3 patents issued on the technology, another 3 pending. They're quite general. They're based on imaging flowing sample stream with any kind of an illumination device detected with any kind of a digital camera, illuminated by, well, as I said, anything you want to illuminate it with. And so we have a picket fence of intellectual property protection around the technology. Now, our areas of interest aren't confined to this one particular application, although I'd say this is the biggest one on our plate. Another one that we've got NIH funding for is the detection of bacteria in platelet concentrate, and we have a number of blood bank collaborators, particularly in northern Colorado at Poudre Valley Hospital and Bonfils in Denver, that we're working with on this particular project. Other applications that we've considered that are on our plate, but we don't have the time and resources to spend on them include tuberculosis detection, water pollution, and food processing. And a couple of these we've licensed. Now, if we look for if it's one primary application, and just consider for a moment the fungal detection to look at how big the market is, there are a little over 4,000 non-federal short-term acute care hospitals in the U.S. And if we marketed the hardware at $40,000 a machine, which I think is a fairly decent price and one that I could sustain in an argument, we'd have a total market of 162 million, and at sales rate of 10% of that a year, we could conceivably ramp up to 16 million a year in the hardware. This also involves selling cassettes of proprietary dye cocktail, and at 660,000 cases of sepsis a year in hospitals times $25 per test, which is an allowable payment under Medicare, that would generate a revenue stream of another 16 million a year just for this one application. So over the last several years, we've been able to raise over $1 million through corporate R&D funds, 2 phase 1 SBIRs, and with that we've been able to test alpha and alpha plus prototypes of the device, which work well in the lab. We have, as I said before, been granted fundamental patents on the technology. Some of the technology has already been licensed in specific areas. We've built collaborations with physicians and blood banks, including the blood banks I mentioned. And then on the fungus project, one of our collaborators, for example, is the chief of pathology at the Cleveland Clinic. And so we've been able to work with some very, very talented people on this problem. And we're ready to start beta testing. So with that, I'd like to open the floor to questions, if anyone would care to.
Yeah. Could you describe a little bit about your business structure at this point in time in terms of how many people, what your focus is?
How many people? 1.5. And so we ramped down on both. basically, we're dependent on contract funding. And so we finished up 2 SVR phase 1. I just talked to the funding officer at NIH, and we were right on the bubble. She thinks they might fund us anyway with money left over from the end of the fiscal year for phase 2. So that will enable me to go back and hire additional people. But we go through ups and downs that are entirely based on contract funding.
Other questions? Great. Please join me in thanking Paul.